Hello and welcome to today's tutorial. And as you can already see in the title, it's a session 1. So that means we are talking about a series of motor protection tutorials in this part of our smart infrastructure, electrification and automation webinars. Today, we will start with the device selection for motor protection and some of the main protection tasks. I am Michaela Mönikers, sometimes a tour guide on the Siemens booth and sometimes a guide through webinars. And so let's start with a short glimpse into the agenda. What can you expect from us today? You will first see an overview of motors and the C-Protect protection devices. Then we will see some information around short circuit protection. You will see CT dimensioning in the configuration in DIXI 5, and you will see the thermal overload protection and the configuration in DIXI 5. And we will not put this tutorial into one big block, but we prepared 2 little breaks in between, and each break is your chance for receiving answers. So if you type your question to the speaker in the question to the speaker field, I will read this question in one of the breaks, bring the question to the expert, and hopefully he will be able to deliver an answer to it. And yes, I think so. In the last times, we often received a lot of funded answers there. So I'm pretty confident that you will receive answers. So just make use of your chance, type your question to the speaker in the dedicated field, and I will be your voice at the end of the presentation and in each break and read your question aloud. And I've mentioned quite a few times an expert. So I'm really happy that today here in the studio with me is my dear colleague, Klaus Wagner. Klaus, please join me here on stage, because I'm not the expert, but Klaus is the expert, my passionate protection engineer and definitely an experienced technical consultant for transformer, generator, and motor protection. So I think by now you are hopefully curious to learn about motor protection. Klaus is anxious to present his knowledge and to share his knowledge. So Klaus, the stage is yours.
Thank you, Michaela. Yeah, hello and welcome to this tutorial also from my side. My name, as Michaela mentioned already, is Klaus Wagner, and I'm the Product Lifecycle Manager for Motor Protection in the C-Protect 5 relays. In this tutorial, we would like to present and discuss the motor protection functions of C-Protect 5 in detail. We have planned in total 2 sessions. In the first session today, we will talk about various aspects of short circuit protection and the thermal overload protection for the stator. In the second session, coming on the 2nd of May 2023, we are going through all aspects of thermal protection of the rotor and also show you additional functions and handling features. Finally, we plan to go through the complete configuration of one specific application example for motor protection and discuss its settings. For this tutorial, we plan 3 parts, as Michaela already mentioned, with short breaks in between them. In the first part, after the introduction, we talk about short circuit protection possibilities for motors. Thereafter, I will show you how to select and correctly dimension the current transformers, and we will go through DIXI, where I show you how to set up the configuration for the discussed relays and protection functions. In the third part of today's tutorial, we explain the thermal model, which is the basis for our thermal overload protection function for the stator and also for the rotor, and explore the features of these functions and its settings. So let's get ready, enjoy the show. First, I would like to give you a short overview of the motors we protect. We basically have 2 different types we can protect with our C-Protect 5 relays. This is on the one hand the induction motor or asynchronous motor, and on the other hand the synchronous motor. Let's start with the asynchronous motor. The asynchronous motor consists of the stator, as you can see here in the picture on the right-hand side. And we have here the three-phase windings, so it's a three-phase system. They are located not all on one place, but they have a symmetrical order with an angle of 120 degrees in this example. And these three windings create, with a current that flows through these windings, they create a magnetic field. And this magnetic field rotates. Inside we have the rotor. The rotor is mostly a short-circuited squirrel cage, so-called squirrel cage, with also the possibility, or sometimes the built variant, that we have a wound rotor with slip rings. So then I have really windings in the rotor, 2 phases or also 3 phases. And these windings are brought outside, where there is normally the possibility to connect a resistor to make the startup easier, because with the resistor we can increase the torque at the beginning. The principle now is the following. The rotor as such is unpowered in both cases, so there's not a current source or a power source that drives a current. No, it's unpowered, and it's like, for example, with a squirrel cage, it's just this cage with iron bars, and we have rings at the end, at both ends, to make the short circuit of these bars. And what happens now is that the magnetic field of the stator rotates over the rotor. The frequency of that field, of the rotation frequency, is basically the network frequency, or we say also this is the synchronous frequency. So this magnetic field creates currents in the rotor, and due to the Lenz's law, then the rotor gets a force which drives the rotor, which accelerates the rotor in the direction, the rotation direction of the magnetic field of the stator. Yeah, because there's a current induced in the rotor at the end. The rotor frequency, so the speed of the motor at the end, depends basically on 2 basic things. One thing is the number of pole pairs we have in the stator. Here it is a little bit simplified. We do not have just a winding here. Normally we have a winding on each side opposite, and then I have a magnetic field going inside here across the rotor. Here we could say we have 1 pole pair. That means I've just the 3 phases. If I have more windings inside, more pole pairs, then I will slow down the rotor speed by the number of pole pairs. So I have to divide the synchronous frequency by the number of pole pairs. Then I get the synchronous frequency of the magnetic field that rotates over the rotor. However, the rotor as such never reaches exactly this synchronous frequency, because it needs a current to be induced, because the current is needed to drive the rotor, to drive the machine. Or if the rotor is just stand alone, there's also friction in the bearings, for example, and so the rotor speed is always a little bit slower, so that the stator field, which still then rotates over the rotor, creates an induced current, which then with a force drives the rotor at the end. Here I have a characteristic of the torque. So on the x-axis here, I have the speed of the motor, and here on the x-axis it's the torque. And you see, when we have standstill here, I have a certain starting torque, and with the speed going up, then also the torque goes up until we have here a peak, the so-called breakdown torque. And after that, the torque here has a negative inclination, so it falls down. And if I'm at the synchronous speed with the rotor, then theoretically I don't have any torque, but in practice this does not happen. This negative inclination, we can say, is also kind of negative feedback. That means if the motor now needs to deliver power to the working machine, then the rotor slows down with a slowing down of the rotor. Then the frequency goes down here and the torque increases. So it's a counter effect. That means the rotor slows down, the torque increases, and then the machine can bring the power to drive the machine, the working machine, the connected one. This goes until to a certain point, and this point is here this breakdown torque. At that point, if my torque I need to deliver is higher than this breakdown point, then the motor will not be able to deliver this torque anymore. And that means the motor slows down until standstill. I can use such a synchronous machine also as a generator. For this, I need to just speed up the rotor by a turbine, and then the frequency of the rotor is higher than the synchronous frequency of the grid. And then I'm here on the right-hand side of this diagram. So you see it's a symmetrical diagram. What we are talking very often when we talk about motors, it is the slip, the so-called slip. And you see it's defined as the synchronous speed minus the rotor frequency or the rotor speed divided by the, where's my mouse, divided by the synchronous speed. The power range for these induction motors, this is a rough estimation. So I think the majority will be in that range, which is indicated, so between 0.1 megawatts and 25 megawatts. As a difference, we have the synchronous motors. Also here we have a stator with 3 windings arranged in a 120 degrees angle between the phases. Here is only shown 1 winding, so you need to imagine also the other windings, and normally it's also on both sides. So we have talked here also about like pairs of the windings here. Also these windings, as in the induction motor, creates a rotating field. However, here the principle is different. I have also a rotor, but in the rotor I have a current flowing, and this current, a DC current, normally a DC current with a lot of ripples, but the base current is a DC current. This creates a constant magnetic field, a permanent magnetic field. Some motors also have a permanent magnet inside instead of the current. The result is basically the same. So I have a permanent magnetic field here inside. And what is different is that the rotor follows the field, the magnetic field, the rotating magnetic field synchronously. So it's not that the field is faster than the rotor in that case, like with the induction motor, but it's synchronously. And yeah, there is an angle between the rotor and the magnetic field, the rotor angle. And dependent on this rotor angle, this synchronous motor delivers more or less active power into the machine, into the working machine. The bigger the angle is, the more power this motor can deliver. We see also here 2 types of motors. On the left-hand side, we call this turbo machine. So here I have really just 1 pole pair. And on the right-hand side, we see a rotor with these kind of noses here where we have the windings around. This is called a salient pole machine because of these noses here. And if we want to have more than 1 pole pair, we need a frequency, a rotation frequency, which is lower than the grid frequency. Then we can do this with adding pole pairs, and the more pole pairs I have, the slower is the rotation of this rotor at the end. So the rotation speed depends on the synchronous frequency, of course, so the frequency I bring in, and the number of pole pairs, as already explained. The power range here, this is also more like a guideline, around 1 megawatt up to 50 megawatts and also above that. So as a tendency, the asynchronous motors are more on the lower part of the power, and the synchronous motors are more on the higher end to deliver power. Good. I would like to give you a short overview of our motor protection relays in the C-Protect 5 family. I've selected 3 categories. Also here, this is not really binding or a strict separation between the 3 categories. It's also flowing, and the application of the protection function depends also on the importance of the motor and how much the motor costs and the process, how important this is behind. finally how much money I want to spend for the protection of these motors. So for the, let's call them small motors, I've just, as you can see here on the slide, a current transformer, and I just take these currents to make all protection functions. Here we have on the one hand our 7SX800, our compact device, the Protect 5 compact device. This is also kind of universal device. That means it is not just a motor protection or just an overcurrent protection. This device can take all the functions which are in the library of CProtect 5. So it takes a subset of all the CProtect 5 protection functions we have there. The subset is formed by the limits of the hardware mainly. So universal device, because you can run this device or load it with just functions for overcurrent protection, for motor, even we have capacitor bank protection functions inside and more. So therefore universal device, and if we load the motor protection functions, this is a good starting point for, let's say, the lower end of motor protection here. Then we have the so-called CProtect 5 non-modular or non-expandable devices, 7SK82, and also a universal device, 7SX82. SX82 universal device, same principle or similar principle as with a compact device, 7SX800. Also here, the functions we can load into this 7SX82 is mostly free. However, the device cannot be expanded. So we can also load here protection function inside. Optionally, we can also use, of course, our bigger devices, the 7SK85, 7SX85, or even the 7UM85. The difference between these and the 82 series is that these are belonging to the classical CProtect 5 devices, so they are expandable. I can add hardware, as you can see here. There's one more hardware module added, and with this additional hardware, I have also other options for the front panels. For example, here we have key switches. So if you want to control and protect in one device, with this expansion module, you get key switches if you like. Okay, this is for, let's say, the simple application where we have just the current measurement. Let's go one step further. Now we include also the voltage measurement here, and we said, okay, this is then maybe for the next higher class of motors in the range you see here. Again, this is just a kind of guideline. What you need as protection function depends on the situation as such. Again, SX800 can also take voltages, and we can make here the voltage-related protection functions. So for the motor, this is basically the under voltage protection. SK82 as already explained, and also SK85, 7SX85, and also the 7UM, when we need current and voltage measurement. And finally, here the difference is that we have here another current transformer. So the idea is that additionally we use here differential protection, so a motor differential protection. And for this we need two current inputs, so two sets of current inputs. And we don't have this with the SX800 or the non-modular devices. We need to go for the modular devices. Therefore, we see here only the 7SK85 or the universal device now, the 7SX85. They are both good for asynchronous motors. We did not talk about that difference. In the past, we said, okay, for the synchronous motors, we have only the 7UM85 because it's a dedicated device for generator protection with all the various functions which are needed on top of that for the generator protection. And this device, 7UM85, has also the motor protection function included. In the near past, let's say recently, we added also protection functions for synchronous motors in the 7SK85. So now we have there also the out-of-step protection and the under-excitation protection, for example. And in the 7SX85, of course, there's everything possible to load inside, so also the complete scope of 7UM85. So therefore, this is also suitable for both types of motors at the end. So these devices, the modular devices, when we need a differential protection because we need a separate current transformer or a second current transformer. Let's have a look on the ATEX certificates. We have also ATEX certificates. ATEX is French and stands for Atmosphère Explosive, so explosive atmospheres or surroundings, environments. And here we've basically 3 different types of devices. The one is the C-Protect Compact. So this is not, as you can see here from the name, this is not belonging to the C-Protect 5 family. It's the predecessor of the 7SX800. And here we have an ATEX certificate. Then we have, for the C-Protect 5 non-modular devices, we have the 7SK82. And for the modular devices, the 7SK85 and the 7UM85. Why do we limit ourselves on these 3 device types? Because the ATEX certificate is a relatively a procedure with a lot of effort, and there's also money behind. And we need to certify a certain firmware version and also a certain hardware version to get this certificate. And we have to prove that basically our relay has a certain outage rate which is lower than a certain percentage. So there is a still 1 level behind. And not in order to do this for every firmware and every hardware and every device, we limited the selection to these device types here on the slide. Therefore, we have also a special ordering variant for these devices. So they come with a dedicated firmware, and you can not change the firmware or upgrade the firmware without losing the ATEX certificate. The same is for the hardware setup. So this concerns mainly the modular devices. Also here we have selected a series of device types from a small hardware setup to a larger hardware setup. And also here the hardware setup is fixed because we need to calculate the outage rate for a certain hardware setup. And we cannot do this generally for all combinations we can create with the C-Protect 5 toolbox at the end. So just these to be remembered when you use such a device. You should not add hardware modules and you should not upgrade the device. It is possible because it is just a device as any other device of the C-Protect 5 family. So there is not a special blocking of the firmware or something inside. We did not do this. You get this special certificate for a dedicated version, and you can order this dedicated version. Along comes also a manual where there are some additional information, some additional things to observe when you use a device as an ATEX certified device. Okay, let's talk a little bit about protection functions. What kind of protection functions or problems do we have? Type of faults. On the one hand, we have short circuits, 2-phase or 3-phase short circuits, and therefore we have a short circuit protection. We are talking about this today. Here mainly the overcurrent protection for the motor or the differential protection. Then for earth faults, here it depends if we have a grounded start point or low resistance grounded start point or an isolated or compensated network. For the first option or principle, we have just an ordinary overcurrent protection for the ground current measurement. So you see here the 51N. For the isolated network, we have special functions, isolated and compensated networks, as we use them also in distribution grids. At least here in Central Europe, we have a lot of distribution grids which have Peterson coil grounding. And it's basically the same function we can apply. It's a directional sensitive ground fault protection, which is a little bit more complex and complicated. Okay, we have a thermal overload of the stator. And this can happen during the operation normally. So not during the startup. The startup is more stressing the rotor. During normal operation, if the current is too big, the load is too big over a longer time, then I can overload the stator. And therefore, we have a thermal stator overload protection function. Then The same for the rotor. So for the rotor, we can have, on the one hand, a too long or a blocked rotor, too long startup of the rotor. For example, if the voltage on the motor is too low, the torque of the motor goes with the square of the voltage. So that means if you have a voltage drop of 10%, if just 90% of the voltage, then the torque will be only 81% of the nominal torque. So this is relatively sensitive, and therefore it can happen that I have a too long startup of the rotor, or even the rotor does not start up at all, the rotor is blocked, or I switch on the motor too often, too frequently, or I overheat. I have the possibility to overheat the rotor. Therefore, we have here also dedicated functions. Then negative sequence currents we get when we have the loss of one phase, or if there's a voltage unbalance. Therefore, we have a thermal model for the negative sequence currents influence. Increased load situation. Here we have the so-called load jam protection. This is a simple overcurrent protection which is activated when the motor is in the running state, when the motor is running. The undervoltage protection, as I already mentioned, if the voltage is too low, then I might not be able to start up the motor, then I can trip the motor. And yeah, then we have some additional functions which have not directly something to do with the motor, but with the connected load, with the connected working machine. On the one hand, if this machine is not loaded because something in the process goes wrong, then there might be the danger that you destroy this machine, a pump, or unloaded drives, for example, compressors. And in this case, can you take out the picture, please? In this case, I will see a current which is too low compared to the normal situation. So we can detect these states with an undercurrent or an under power protection at the end. And then finally, bearing overload. Don't know what you mean, Gerd. Bearing overload, so I got some instructions which I don't understand, don't care about that. Bearing overload, therefore we have temperature sensors, RTD sensors, which are there on the bearing, and we can get this temperature and then give an alarm or even trip the motor if this is too high. Then for the synchronous motor, I have additionally the problem that the synchronous motor is not synchronous anymore, but falls in an asynchronous state or slows down. Therefore, we have the under-excitation protection and optionally the out-of-step protection. And often there's also used the rotor ground fault protection. Yeah, that's it. So in the session 1, we talk about the 3 first principles and protection functions. In the session 2, I plan to cover the rest, except the synchronous motor, because there we need more time, so I leave that out. Here we have a motor start current, startup current. You see the timing. We have here something like, it's a very fast startup, couple of seconds here. This can go also for 20, 30, 40 seconds, depending also on the motor type and what is the voltage which I apply to the motor, how big is the load. But in that range, so between a couple of seconds and maybe a minute, something like that. What is characteristic is that at the beginning we have a peak here, you can see that, kind of inrush current, and then we have a relatively stable startup current, and only when the motor reaches its final speed, then it goes down, and then I have here a current which drives at the end the working machine, and the amplitude of this motor, of this current depends on the load I have connected to the motor. The amplitude here during the starting does not really depend on the load. The length depends on the load. So the heavier the load, the longer is the startup process, the slower is the frequency difference, the speeding up of the motor. But basically, I have a relatively constant current during the complete startup here. So this is the scenario. This is the scenario when we connect the motor directly to the power, to the bus bar via a circuit breaker or a vacuum contactor. When we have variable speed drives, then the story is different. The variable speed drive controls the frequency during the startup of the motor, and then yeah, the picture looks a little bit different here. Okay, let's come now step by step to the protection functions we can apply. And here I have an overview for you. For the situation of a motor start, we see here the peak of the motor, this inrush current, and the relatively stable motor startup current, and then it drops down to a certain load current when the motor is running constantly. And I put some typical values in. So the startup current is around 3 to 8 to 10 times nominal current of the motor. So as an average, something like 5 times, 4, 5, 6 times nominal current. And for the startup time, I gave you already some ranges, a couple of seconds until to, I don't know, a minute maybe. And I have a certain value here. Again, the amplitude of that current depends on how big is the load on the motor. So how can we protect now? We have to consider always that the motor has a running phase, of course, and also a startup phase. So our protection functions must somehow adapt to both situations. And yeah, the first thing what we can do is to put a high set element, an instantaneous stage here, on top of that peak current, peak starting current, so with a certain margin here, with a certain leeway, and yeah, undelayed, because here I want to trip immediately because I don't need to wait. I will not pick up here with a starting current because I'm above this maximum current. Then during the startup phase, I can set a stage that is relatively close to the startup current with a certain margin. However, here I need to consider a certain time delay, of course, because otherwise this peak here endangers to get the wrong tripping. And then finally, yeah, as a backup, we can say rather the last thing before everything breaks down, we can also add a definite overcurrent time protection function with a long delay time, which is active only after the startup process has finished. It depends if you have a relatively fast startup process, like a couple of seconds. This makes sense. If your startup current is, I don't know, startup time is half a minute, I don't know if it makes really sense to add here an overcurrent stage after half a minute. Also here, then I need to have a certain margin to the load current, the maximum load current, but the thing here is that I'm lower with my setting than the startup current. Okay, in this picture we have also some thermal functions. They are not exactly like that because the tripping time here depends normally on the load we have before. So how hot is the stator or rotor? But we put it inside here, so they have a longer tripping time normally for the rotor and for the stator here. Additionally, if we have a differential protection, now you see we have the big advantage. We can set this stage to a very low value below the load current here. And for this, I can use the differential protection. And I have a second one, the faster one, which I would like to put over the starting current. And finally, we have the load jam protection. The load jam protection you see here cuts the starting current, so this would give an unselective trip during the starting phase. Therefore, the speciality of that function is that it's activated only when the motor is securely running. So I need to place this also over this maximum current, but with a relatively short delay time, so that yeah, it's activated only during the motor running state, so it will not be affected by the startup current, and I have some short delay time anyhow, which I explain in the second session, so stay tuned and wait for the second session. Okay, protection. This is again the curve we had before. So I said we can put here a fast stage, instantaneous stage without any time delay, and a recommendation or an idea could be put it over 1.3 times, so with a 30% margin here on the maximum transient current. If you don't know something about this transient current, either you make a fault record during the commissioning and then you see what's going on in the motor, or you say two times the startup current and you're on the safe side here. Okay, recommendation here is to use RMS values. Why? Because we can have saturation of the current transformers, and then some part of the current breaks off and cannot be seen on the secondary side of the current transformer anymore. However, if I take RMS values, then I get the full, let's say, RMS value of that current which is remaining. Whereas if I put also a filter on this already cut off current, then I get even less current. So this RMS value evaluation works against the saturation of the current transformer, possible saturation of the current transformer. Then for the second stage, again, we set it over the startup current here. Also here, a good practical value could be 20% above the startup current here. And here we need the time delay. Here the recommendation is to use a fundamental evaluation because it reduces the effect of the DC currents. Okay, however, during the commissioning, you should verify that. Could you please take off the prompter text here, because this is absolutely irritating me. I have here still the last line of my introduction, so this really irritates me. So otherwise I cannot look into the camera anymore. Okay, so during the commissioning, it must be verified that the delay time of this stage here, so here, that it is longer than my peak. I can measure this during the commissioning and then adjust it. A good value here. A good value here is basically 100 milliseconds. Good. And for the last one, yeah, if you have short starting times, this could make sense. You put an overcurrent stage here, also 20% over the maximum expected load current here, and a long delay time so that you don't trip during the startup of the motor. So this is a slow backup function at the end. Okay, if we want something faster and something more sensitive, you see, we have basically with the fast overcurrent functions to go over the starting current. Then we can use a differential protection. Before we go on this differential protection, let's have a look on the possible fault locations. A differential protection, a classical one, distinguishes between a fault inside and outside. Inside is in between the current transformer, and outside, especially behind, is outside. So how is the situation here? I put here 3 fault locations, and fault location 3 is outside of the range, obviously. However, for all faults, I need to open the circuit breaker in front of the motor. So it doesn't really make a difference if I have the fault behind the motor or inside this field, or if the fault is outside here, and then I won't see any current at all because there's no in-feed from the motor, with one exception, that the motor feeds the fault, but about this we will talk probably in the second session. Okay. The purpose of the differential protection, so what is it? It is to be more sensitive than the overcurrent protection to detect small currents during the startup and during the operation of the motor. So typically 20%, 0.2 times of the nominal current of the motor can be detected. It's a standard setting we have. This is the purpose here during startup and during operation. Disadvantage, I have more effort. I need an additional current transformer. I need a differential protection function, and so on. Good. We have basically 2 principles we find with a motor differential protection. The one is shown here on the left-hand side. It's the classical one. Here I have the 2 current transformers on the terminal side and on the star point side of the motor, and I have a differential protection function in the relay that works as a differential protection, phase selective, so I need a current transformer for each phase on both sides. Differential protection is calculated by the relay. We see this in one of the next slides, how this is done. As a difference, we can also have the following principle. I have here a current transformer. You see it's a second one. This one will then take over the standard motor protection functions like overload. And with this current transformer, this is a so-called window type current transformer. Here I need, basically behind this symbol, we have 3 single-phase transformers, so transformers with a hole inside, and they will bring the current of the phase one into one direction through that current transformer, and you go back again before you make the start point. Here, okay, the backwards cable is not going through the motor again, so maybe that's not correctly drawn. It goes around and you guide it back, and we have 3 of them. Since they go in counter direction, they eliminate each other, the currents in this current transformer. So the differential protection is formed basically in this on the primary side in this current transformer. And what we have to do is to evaluate an overcurrent stage. Here additionally required on the left-hand side is a current transformer in the start point and a differential protection function in the relay, whereas here additionally I have this window type current transformers, 1 per phase, and I have to bring the cable backwards, so I have also a little bit higher wiring effort at this time. The protection function here is a classical overcurrent protection function, so just one stage, because the differential calculation, or I don't know how to say that, it's not a calculation, the forming of the differential current is done here in this current transformer by the currents which flow in opposite direction. Good, these are the 2 basic principles we have, and yeah, I would say they are more or less equivalent. You see now the differences in the setup, the effort we have, and yeah, for the window type current transformer, we need a simpler protection function, overcurrent protection instead of the differential protection, basically. So how does our differential protection function work? First, it is like the transformer differential protection function. It's a subset of that function. We took that function and took out all the stuff we don't need for motors. For example, a vector shift compensation, or the start point compensation, the zero sequence current elimination. This is all not required here because we have just a current going in and out, and we have a galvanically connected motor wiring here between both. So there is all this nice stuff we have with the transformer diff protection we don't have here for the motor protection. In ZProtect 5, we calculate our stabilizing current with the maximum of all currents, always per phase. You have to think here in per phase. It's one of the 3 principles we can have for stabilizing currents. The other one we find in the ZProtect 4 relays, where the stabilizing current is the sum of all currents, of the amplitudes of all currents. And the third one, a similar thing we have in our restricted ground fault protection, just besides. The differential current is always the sum, the vectorial sum of all currents here. Under normal operation, the current that flows in flows out here. Motor is running, all protected object is delivering power. So the differential current is 0, and the stabilizing current is the maximum of all the currents which we have here on our object. I don't have a tripping quantity because I have no differential current, theoretically, ideally. If I have an internal short circuit, which is fed from both sides, then I can have, with that method, also a stabilizing current, a differential current that is twice, in the extreme case, twice as big as the stabilizing current. This comes here from the calculation of the stabilizing current, as you can see here. This does not apply for motor protection because we don't have an infeed from the start point side into the motor, so we don't see that here. What we see is for an internal short circuit, the side current here is 0, and then the differential current is equal or identical to the stabilizing current. Okay. For the differential protection, we need to be stable against external faults. Therefore, here this drawing, basically we have to distinguish between high current faults and low current faults. For the high current faults, the CT saturation makes us a problem because there's a high current. For these low current faults, we could get also problems with the current transformer if there is a long DC component in the current, and then even with a small current, it might happen that one current transformer of the 2 will saturate. and this also could create us problems. Yeah, I went over my here animation. Anyhow, for the motor differential protection, we use the same principle, although, as already mentioned, we don't really have external fault, so we need to replace external fault here always with the starting current of the motor. This is what endangers the stability of the differential protection. Okay, this is the tripping characteristic. We have basically 3 sections. Here, first we have a threshold, and this is one stage. We have also a second stage. About this I have slides here. We have a threshold here. We have a section with a certain slope, slope 1, and then a second section here, the blue marked one, with a higher slope. So the slope 1 is normally to compensate linear influences, and the slope 2 is again to compensate more against current transformer saturation. And then you see here an add-on stabilizing area. This is also used to overcome problems with CT saturation, current transformer saturation, because if we have external faults or not a faulty situation, then I will not have a differential current right at the beginning. I will get a differential current because one current transformer saturates after some time, and the trajectory will go in here and then go up. And if we enter here that area, the tripping area, then we will block this tripping for a certain time because we know, we went here through this add-on, through this section here, so this cannot be an internal fault. Roughly spoken, I cannot go into the details here. Maybe we make a webinar about transformer protection in the future, then this would be a topic to go here really into the detail. Anyhow, here are the standard settings, and the good news is normally you can just go with these standard settings, leave them as they are. They are kind of practical values which we gathered with a lot of tests, a lot of different scenarios here. So if you don't have something special in mind, you can just leave these settings as they are. So very comfortable and pleasant. With one method or one principle which we applied especially for motors, and this is the startup recognition of the motor, because the startup procedure can be very long, and if we have current transformers, maybe with the remaining remnants, maybe on one side more than on the other, we could get also problems. And the idea here is to make our relatively sensitive differential tripping characteristic less sensitive during the startup. That means my threshold and the slope 1 value are increased by a certain factor which I can set, and I make this, so I jump up here with my characteristic for the starting procedure, and when the starting procedure is over, that means the motor is running, then the characteristic falls back to the more sensitive characteristic here. There's a little bit to read in the documentation if you like afterwards, so it's basically what I've already explained here. So, and with that, we are at the end of the first part. Are there any questions?
Yes, there are. Some of them are, that's fine.
It's okay.
It's okay to go like this. There we go. And let's see, let's jump into the questions. And there are already some. So thanks a lot for handing in your questions. And now let's see. Klaus, OY wants to know, what is the motivation behind for an ATEX relay? Normally, the relays are in the electrical room, which are not in explosive zone 0, so X zone 0. Is a protection panel near the motor considered?
Not really. So our ATEX certificate is basically, there's the camera, right?
Yes.
Our ATEX certificate is for the installation of our relays in the zone. Now, I'm not 100% sure the one which is not in the really dangerous one, I think is the zone 2 or 22 or something like that. That means it's away from the critical process, but it protects a motor which is in critical process, and therefore we have some requirements for the relay against failures, breakdown of the relay outages, and we have to ensure and prove when we make this certificate that the relay is able to operate in a relatively reliable way. So what we have in the relay is nothing different to our standard relays. The difference is that we have to certify that, to prove that, and this is also then verified by an institute, and this is the procedure which is behind the ATEX. So it's not that the relay is in this special zone, in this critical zone, it's away, but it protects the motors which are in this zone. And one principle is, for example, that if the relay is defective, is broken down, that it must trip the motor immediately. Yeah, so it is a thing of the reliability.
Thank you.
Mm-hmm.
And then SKG wants to know, is it possible to share the slides or related information via email? And yes, that's exactly what we are going to do. And you will even receive a download link. So you do not have to wait for the mail, but you will get access to the presentation and to the recording. And then we come to the next question. And by the way, it helps us a lot if you put the questions I shall place to the speaker in the question to the speaker field, because that's what I monitor during this questions round. I have a kind colleague in the back who copies if you put it into the chat and copies into this questions field. But if you just put it right there, that'll be perfect. Other way around, we will also find your question. So let's start with the next one that was kindly copied here. Can I run 2 or more motors with just one C-Protect 5?
Yes, that's possible if we use the expandable devices, so the 7SK85 or 7SX85. There we can add more current inputs because it's all the basic functions are based on the currents. And yeah, then we can set up a set of functions for the first current input, for the second, which is then connected to the second motor, to the third motor, and so on. The maximum number I don't know at the moment, because this depends how many functions we have enabled, how many. Yeah, and it depends also on the load, the processor load of the relay, so this needs to be tested. I know for a simple overcurrent relay, I already made configurations to protect 10 feeders with one overcurrent relay, C-Protect 5. So I guess, but that's just a guess, that it is in the same range with the motor protection. Again, I have to check how many instances of motor protection functions we allow in the relay, but it is possible, basically, yes.
And perfect, because that just brings me to another information for you, because Klaus will get some homework. So he just mentioned, I have to check that. So you will also get a written answer to these questions, and then you see exactly how many motors we think can be handled with one protection device. And then the next question just fits into the same row. Is there a provision to synchronize 2 motors with a protection device without a master controller?
To synchronize 2 motors? No, I'm not really
feature,
sure
right?
what you mean exactly. If we talk about busware transfer schemes, or maybe we have to discuss this, so I don't understand the question at the moment.
Because I also think that the synchronization of 2 motors is more a control from the process, and what you just presented is the protection of the motor. So it's electrical protection, right, mainly. So, but we'll investigate on that. And maybe this is a question where you two get in direct contact and clarify exactly what you mean, what the task is, because that's also possible. I think you will receive Klaus' contact at the end of the presentation. So stay tuned. And we go to the next question. SKG wants to know, if we use variable frequency drive, where do we place the CTs and the PTs for the protection?
Directly at the motor, because all the thermal stuff we have with the motor and also the overcurrent protection, if this is not done already in the frequency drive, then we place the protection device directly at the motor. The frequency, the startup frequency is increasing, so it starts from a very low value, of course. That's not a problem because from 10 Hertz upwards until 80 Hertz, I think, we have a frequency tracking. That means we monitor what is the network frequency, and we adapt our sampling rate so we can cover the complete range of this frequency when the motor is starting up. And the protection relay reacts as if there were just 50 or 60 Hertz, so we can cover that complete range. And below 10 Hertz, we don't have this tracking anymore, but the overcount protection, for example, is nevertheless active. If we go to very low ends, and it's not that precise anymore, yeah, because we get then fluctuating currents. Let's say we see fluctuating currents even if the amplitude is fixed, but it's still a protection and it will work, but it will decrease the sensitivity. So if we go down to 0 Hertz, of course, we don't see anything anymore, but we can cover that.
Thank you. And then the next question came in from OY. Thank you for that. What should be the overcurrent element setting for a differential protection using window type CTs for each phase?
Yeah, this I forgot to mention. Yeah, so our classical diff protection, we recommend the 20%. So we can also go for 20%, for example, or even lower with a window type CT. You can test this out during the commissioning. If you make startups with a motor, then just register what does this stage see. So with a fault record, what do you see in each phase on this current transformer? And then you will see there is a small rest current anyhow because of unsymmetries, whatever, between the two phases, the location of the cables in this window type, CT, and so on. And then just go over this threshold with a good margin, take the double value. So if you see something is 5%, you can take 10% as a threshold, and then it should be fine.
All right, thanks. And then we take one last question before we go into a short break. So AN wants to know, what are the capabilities for C-Protect 5 motor protection for thermal image modeling of the motor and the number of starts permissions?
Okay, so this is a little bit more complex question. Maybe we can skip that to the end, because then I explain what we have as a thermal image, as a thermal protection of the stator. The rotor comes in the next session, so in May, so stay tuned and also watch us in May. But I will come back to that question at the end, I would say, because then we have a better basis, better understanding what we have. Basically, we have one function for the stator and we have separate functions for the rotor, so we don't mix up everything as other manufacturers do or other principles are. So we have dedicated functions for the stator, for the rotor, and also the negative sequence that affects the motor. Also, this is evaluated separately from each other.
All right. Thank you.
Okay, but I come back to that.
So we need to keep in mind that we need this question again. I try to keep that on my agenda. All right. So as I already mentioned, we would do a short break, get in some fresh air, give your eyes and ear a bit of a rest, enjoy a coffee or a tea, whatever you like, and let's meet again in about 10 minutes. You will see a countdown.
10 minutes.
See you
5
soon.
minutes. Okay.
Oh, that's sporty. 5 minutes is a bit sporty to get a coffee and
you are the boss.
some
10
other
minutes,
things.
it's okay.
Yes. So see you soon. Stay tuned. All right, welcome back. I hope you enjoyed a short break and have now a kind of fresh brain to put in more information, because Klaus will now continue this tutorial around motor protection, and he will share some knowledge on CT dimensioning and the configuration in Dixie 5. So Klaus, let's continue. Stage is again yours.
Yeah. Thank you. Yeah, let's continue with the current transformer selection and dimensioning. What you see here on this slide is an extract of our manual. So in the device manuals of each cProtect 5 device, at the end, we have a kind of table and explanations, and I think also calculation examples, where we define what are our requirements, so for our protection functions, towards the current transformers, that everything works fine, that we do what we specify in the manual at the end, in the technical data. So for the motor protection, we have to consider basically two things. The one is the overcurrent protection, and if we want to apply differential protection, you see here we get different requirements. Just a little bit arranging that again. Good. Yeah. And you see, maybe one more word, we do this for the most common types of current transformers, classes of current transformers, so we get here everything. And I would like just to calculate one example or two to show you how you do that, and that this is really not that complicated. It's a relatively simple thing at the end. Okay, let's start with the overcurrent protection. So this is one example. I have here a motor. Here's some motor data, the current transformer data, and here's the relay connected with 10 meters length of the wiring and a relatively small cross-section of the wiring. So here the idea is this overcurrent protection is close to the motor, so it's installed where the motor is in that cubicle, and the cable to the motor goes out and is maybe not relatively long. Okay, first we have, now I'm talking about these 5P or the 10P relays, current transformers, and there is a required operational accuracy limiting factor, this ALF dash here, and this should be bigger than the maximum threshold divided by the nominal current of the current transformer, primary, but it should be at least 20. So this but at least 20 comes, when I'm correctly informed, from the fact that there can be remnants in this current transformers, and this is all included so that everything works here fine. Therefore, we must think, what is this maximum threshold? If you remember, we said this high set element, we set over the maximum starting current, this transient starting current with a certain margin. And to get this, either you find it during the commissioning, you start up the motor, and then you see what is the peak value here, or we calculate it from the nominal current of the motor. And here is one way how you can get the nominal current if you don't have it via the power here. And in our example, we come to this 107.8 amps. And yeah, the transient current is, if we don't know anything better, 2 times the startup current, and the startup current we find here. So this is all motor data you should somewhere have, or you measure it. The startup current is 5 times the rated current of the motor, or the nominal current. So we have at the end multiply this value here by 10. So we come to a threshold of, to a starting current of 1078 amps. Our threshold we put at 30% over that value, so we come to this 1401 amp. Second aspect, what do we have now in our special setup? So first we need to know what is the burden of the CT, the rated burden. We get here a value of 5 VA. That is a power, and the resistor this current transformer can drive is the power divided by the square of the current. So we can put here a resistance of 5 ohms behind, and then this current transformer will work under nominal conditions. If this was a 5 amp current transformer, then you see the resistance that current transformer can drive is just 1/25. So it divide this burden by 25. Okay, the actually connected burden is this one. It's the burden of the cabling and the relay burden. So for the relay, we find this data in the manual, and for the cable, we can calculate the resistance with such a formula here. I don't go through the numbers now, but I just inserted here this copper constant, the relative resistance of the copper. The length of the cable and the cross-section is there, and if you put everything together now, in our example, we come to this 0.27 ohms. Good, so now we know what is the actual connected burden, and now we have to go back and have a look, okay, what is our requirement? No, first we calculate the actual operating accuracy limiting factor. So this we can do now with the data we have before. I've here the relay internal resistance, which is a given data here, and the nominal burden. And here in the denominator, I have here the actual connected burden. And you see the operating accuracy limit factor is normally bigger than the nominal one of this current transformer if the connected burden is smaller than the rated burden, which is the normal case, how you normally use such a current transformer. And then we get here an ALF dash of 40.1. That means if I bring, what is the meaning of that? This ALF, which is this 10 P10 here, means the second 10 here is important. At 10 times nominal current of this current transformer, this would be 1,500 amps. This current transformer can transmit a sine curve current without saturation. It's just starting with the saturation. And instead of the 10, now we have 40. That means a sine curve without DC part in the current can transmit 40 times, can be transmitted up to 40 times the nominal current, 40 times 150 amps. So this is the meaning of that value here. Good. What is required now is, what we have here on the left-hand side. This is what we see in the manual. This is what we can calculate from the first term here, 1,400 divided by 150. It's 9.3. But it should be at least 20. So here the 20 wins. So it must be bigger than 20, bigger equal to 20. And we make the comparison. So we have an ALF dash of 40.1. We need only 20. So we can fulfill the requirement and everything is fine with this current transformer. A short remark about the CT range, about clipping. For the overcurrent protection, this has no significance. That is not important because we always get a current that is bigger than our threshold and the overcurrent protection will trip. For the differential protection of a transformer, for example, this is one aspect we need to consider because I have different current transformers on both sides of the transformer and the range can be also different, because the nominal current of the current transformer is not ideally adapted to the side current of the power transformer. And there it would make sense to have a look on that. Here it's just to mention one basic principle, so an add-on, which does not concern us really for the motor protection, and it is the CT range. That means how big is my current, the maximum short circuit current, which I have here as an internal fault. And does this relay still see that fault current? And for this, we can take simplification. So either you have a full scheme calculation of your maximum short circuit current with a program, or you make an estimation. If you have a transformer upstream to your location, you can get the maximum short circuit current behind the transformer by dividing the nominal current of the transformer over USC, so this relative short circuit voltage, which has values like 0.1, 10%, 5%, 15%, something in that range. And here expressed with the power of the transformer, so you get here a certain value. In our example here, I just put what I thought reasonable values as a transformer in front of that. We get here 9,100 amps as the maximum short circuit current behind the transformer. This would be something like 61 times the nominal current of the current transformer. And here we see the SK82 goes to 50 times nominal current with a measuring range. This has nothing to do with saturation, it's just the dynamical range of the AD converter. So here we have 50, the current is a little bit bigger. So we would here already encounter a little bit clipping. Again, this is not a problem for the overcurrent protection, and for the differential protection, neither, because I have the same behavior on both sides. And we don't have external faults for the motor protection. So this could be a problem if we have external faults. The startup current is never that big normally. So for the motor protection, this has no significance. I thought I put it anyhow here just to make the picture complete. Another point is to check if you have the maximum fault current do you not overload the input of the protection relay? This is normally not a case, but in some special cases, this could be also an additional aspect if you think about current transformer dimensioning. Okay, here again, once more, I repeat it, this CT range has no significance for the motor protection. Okay, let's have a look. Second example. Now I did not exchange here the data, but instead of that data with a 5 or 10p current transformer, let's now have a look on a class PX current transformer. So there we have a knee point voltage, and alternatively, on the other hand, ANSI class current transformer. The required knee point voltage, this is also what you find in the manual. I just copied it out from the manual, is here what you see in this formula. And you see also here we have always this maximum threshold divided by the primary current and a fixed value here. So the formulas look a little bit different, but if you can recalculate this to the 5p, 10p world, and then you come basically to the same requirements, must be the same requirements. In the ANSI world, we have the so-called terminal voltage here. And here also we have a formula. You see here it's the 20 again. Here it's a little bit smaller. This has to do that the point where the 5p, 10p current transformers start to saturate is defined in a different way as the knee point voltage. Therefore, we have here another factor basically inside, but the calculation is, the way of calculation is the same at the end. So now we talked about the requirements here. Then we have here our maximum threshold. This is what we had before. And now we have to have a look on the actual connected burden. I took here the same example. Yeah? So we have the same burden of the relay and the cabling. However, for the class current transformer, this is a 5 amp current transformer, so my burden in ohm of the relay is smaller. So I have to recalculate that, and in this case it's smaller because our burden in the relay is always 0.1 VA, and this is more or less independent if it's a 5 amp or 1 amp current input configuration in the relay. So we don't have 5 amp and 1 amp relays. It's just a setting in the Dixie, and we can switch over the relay from 1 to 5 amp. So it's more universal, and you don't need so many devices on stock and so on. So this is one of the advantages we have here. Okay, let's have on the left-hand side now the required decay. This is what we basically find here in this formula, and I just inserted here the values, so the maximum current, and here the values of the current transformer, 1.3 ohm, and the burden. And then we come around at 9 volt, but at least 16 times that stuff, so we come to 25 volts. In the ANSI world, we have this terminal voltage, and yeah, I just set in my values here for the required voltage, so I come also to something like 9, 10 volt, and it should be at least 20 times 5 amp times my burden, so 17 volts for these current transformers here. And we see also, if we make the comparison, the required voltage is 25 volts. This is what we calculated here, and what we get here in our current transformer is 100 volt. So I just selected this kind of current transformer. So it's fine, and also on that side it's fine. The required voltage here would be 17.4, and we have 100 volts as this current transformer. Okay, this would be the way to calculate basically with other types of current transformers. Basically, I see what is my requirement. I take that formula from the manual. I set in the values. Maybe I need to have a side calculation to get these values like the maximum threshold. And then I see what I have actually, and what I have actually depends on the connected burden, so the length of the wiring, the cross-section, the power of the transformer, so the ALF, the nominal accuracy limit factor, and with all that stuff together, I calculate the actual operating accuracy limit factor, and then I make the comparison. What do I have? What do I need? And if this is what I have is bigger than what I need according to the requirement, everything is fine. So in that way, without dedicated programs, we can relatively quickly calculate if a certain current transformer fits to this application or not. And in a similar way, we have calculations for all the other relays. Also for the distance protection, we have a certain requirement here, and we just need to always make the same game. So I see what is required. I see what I have with my actual setup. And then what I have must be bigger than what is required. And then the current transformer is dimensioned correctly. Good. One more example for the differential protection. It's another motor here, other values. Here the required factor is 4 times. And now we have to see normally for the differential protection here stands the maximum external current. Now we delete external current and say this is the maximum starting current, the transient starting current, and the 4 inside, but at least 30. Again, this at least 30 is for the remanence behavior of this current transformer so that they work, that the relay works correctly, also with the most sensitive setting, the 0.2 what we have, that this is guaranteed. Therefore, we have also here a constant factor which describes the situation when there is remanence in the current transformer. Okay, the transient starting current, in that case, same calculation, the nominal current of the motor, then I just set here 10 times. Nominal current is my transient starting current, because I have here also the starting current is 5 times the nominal current, so I come to this value here. And then inserting this value, we can calculate the required operational accuracy factor, limit factor. So it's the 7,580 divided by 1,000 times 4. 1,000 is here the current transformer. So it's 30.3, but at least 30. So this time, this number here wins a little bit. Now I have to think, okay, what could I use now for this current transformer? I don't have now a given current transformer. Now I want to select one which fits here. Here I consider the line, the way back here from the current transformer to the relay is relatively long because this current transformer is located at the motor, whereas the relay is located at the in-feed, so in the switch gear. So I have a longer way here. And therefore I say, okay, I want to have a little bit more powerful current transformer. This is first an estimation. So I take here 20 VA instead of 15 VA. And I have here an internal burden which comes from the manufacturer of the current transformer, or we can also measure that. Then the burden the relay can drive in ohm is then 20 VA divided by 1 amp, so 20 ohm. And the actual connected burden now we can calculate in the same way. So I don't go through that example. You can do that if you like. And we come to 1.52 ohms. So it's basically the wiring resistance plus the relay resistance here calculated from a power backwards to a resistance here. Okay, now we do it the other way around because we don't have the current transformer. Now I would like what could be the nominal accuracy limiting factor of the current transformer from the required one. The required one was, we remember, 30.3 here. And now with all the given data, I can see what does that mean for the nominal ALF of the current transformer. So it looks like the formula is the same, but the numerator and denominator are swapped. So I have 1 divided by the term we had before. So here is the actual burden, the connected one. Here's the nominal burden. Therefore, the value is smaller. So I don't need such a high value for the current transformer. I need a smaller one, and the result is 7. So in that case, I could say, okay, instead of 7, I put a little bit margin on top of this. So 10 would be good. So I would then select a 1000 to 1 amp, 5P10, and then the 20 VA fits quite well. So what we need to say for that is I could go here also with 10 VA, but then I get a higher value here at the end. And then I need to select, instead of 5P10, maybe a 5P15 or 5P20. This is now the freedom we have because the current transformers characteristics can be achieved by different levers, but different variables. The one is the power, the internal burden, and also the ALF, so the 5p10 or 15 or 20 after the p, the accuracy limit factor for the contrast. Here we have a little bit freedom. Generally, I would recommend use the same current transformer on both sides. There is no need to use different ones normally, so it makes the thing simpler and more reliable because they will behave in a similar way if there is somewhere a saturation problem or something like that. And yeah, why should you not use the identical current transformers? But as you can see here, this one now is different because here this line length is longer. So it's not a requirement that the current transformer must be identical. They can be completely different. We remember the protection function is identical to the transformer differential protection. So also there we definitely have different current transformers, and so we can use also completely different current transformers here for the motor. The only point is that both sides or all sides must fulfill the requirements for the differential protection, and then we are fine off. Okay. For the window type current transformer, I don't have this example here now. Yeah, it is an overcurrent protection function behind. So we need, in that case, if we make the differential protection with this window type current transformer, we need then the requirements for the overcurrent protection function. Very simple. Good. I have here also another example verifying the current transformer at the in-feed side. I leave this to the eager readers of the documentation and just jump over that in order not to lose too much time here. I just had this here to make things complete. And yeah, we make longer breaks, so I have to save a little bit time. Therefore, let's go to the next point, to the Dixie 5. And I would like to show you here how we can make now the configuration. And for the experienced users of ZProtect 5, I beg your pardon, I will start a little bit at the beginning so that also the people who have never seen the Dixie 5 can get an idea how to do that. Of course, if we go into the details, if we went into the details, we would need much more time. So it's more the guideline, the basic ideas what we have. So I've already prepared here a project with the 3 relays that we can use for our purpose, for the motor protection. And I start with the 7SX800. So if I open this here, I have here the device information. So here I get some general information about the device, configuration version, and so on. And I need that to show you, because I now copy here the MLFB, the product code, to show you how to start from scratch. So if I want to add a new relay here, I go to add new device, then I get here a dialog. I now copy in here my product code. So this product code you can get either if the relay is already on your table, you see that on the relay, or if you start from 0, then we have an online configurator where you can define the characteristics of your protection relay. And from this online configurator, you get this product code. And this is the interface for our Dixie 5. So I put this in here and click on verify. And then the Dixie gives me here so-called application templates. So this is a pre-defined selection of functions for certain applications. And here it's a very nice example, because the 7SX800 is a universal relay. So you'll find here application templates, so bundle of functions for non-directional relays, for a directional overcurrent relay, the one with the Peterson coil, and for example, for motor protection functions, just using currents, using current and voltage, and some other things here. So this is a classical or standard approach we have with ZProtect 5. We offer predefined application templates. Once you have finished your configuration, you can also save this configuration as a user-defined template. Then you don't need to go through that initial process all the times. Then you have already what you really need, and you can start that. Just to mention that I won't now don't want to create a new relay because I've already one. I just wanted to show this to you and save the time. So here we have the device information and we have the concept of the function points. Also a couple of words to these function points. We see here we have a list of functions in the relay, and certain functions here cost function points, not all of them. What is that function point? With CProtect 4, we ordered, or you had the possibility to order bundle of functions, options, software packages like an auto reclosure or a synchro check function on top of the classical overcurrent protection function, for example. Here we do it in a different way. Here we have the so-called function points. That means you buy a relay which has already included a certain number of function points, and then you can use these function points and fill or use these function points with functions you can add to the relay configuration. So every function has a certain value in function points, and this gives you the incredible flexibility that you can swap functions, exchange functions, add functions during the whole lifetime of the relay. So therefore, it's like a credit card or like a prepaid card, better maybe. You have some amount there, like on the mobile phone maybe. There are prepaid cards, and then you can use this prepaid card on the mobile phone, and who you phone with this prepaid card is not defined. This you define ad hoc when you have the idea to call somebody, but you get then the money subtracted from this prepaid card. And here our prepaid card is, or the function points is a bit like this prepaid cards. We have here a budget of function points, and you can use them for whatever function, and this gives you the flexibility to phone to the person A and not to the person B ad hoc, for example. So maybe this is an example. Okay, that's the concept with the function points, just to mention that. Now let's go a little bit more into the configuration. First, we have the hardware and protocols. And this editor for the compact relay, so the 7SX800, is used mainly to define the communication features. So therefore, I click here on my interface. This is now a electrical Ethernet interface here. And if I click here on the properties, then I can select. This takes a little bit of time here. Now I can select what should run on this Ethernet interface. For example, I can select here under communication, the IC protocol 6150, other protocols going to SCADA, whatever you have here. We have here redundancy concepts in all CProtect 5 relays, point-to-point or RSTP, or also the seamless redundancy protocols, PRP and HSR, for example, for those who are familiar with that, and other network services, just to mention this in a quick way. So you don't buy the relay with a certain protocol function as you did this with CProtect 4, but you have then an interface which you buy with a relay. In this case, it's inserted already. In case we have a modular device, you can also later insert this communication module and then define what should run on this communication module in the Dixie here at that place. And also this gives us a really big independence and flexibility as regards to communication features of a relay, because I can change this at any time of the life of the relay. So later, if you think you need to add some additional communication modules, you can just do that, for example. Good. For the, we see that later. For the modular devices, here is also the place to add expansion modules to the device. Good. Maybe a word to the measuring points routing. Here I define what comes to the analog interfaces, to the measuring points. So in case of the 7SX800, I have here 4 current inputs and also voltage inputs. And the application template which I used already prepared me these inputs. And here's the point where I select if I want, for example, to connect just 3 phase currents and the 4th input remains empty, so I can use this for something else. Or if I want to connect the classical Holmgreen connection, where I then measure the ground current formed by the start point of the 3 phase currents, and I go backwards through the 4th current input. So I can also add this, And you see we have here some additional possibilities. Maybe just to pick out one, I can use two primary current transformers only and a separate current transformer for the ground current. So here we define what kind of connection comes to the relay, and the relay watches what is connected here, and the protection functions react accordingly. The same for the voltage. Here we have just the three-phase to ground voltages now connected. If I want to use additionally the VN, then I need to select here another connection type. Good. If we have a look on the settings here, we see we have here some folders. Motor, circuit breaker, these are called function groups in cProtect 5. A function group basically is a kind of container, a box, where I can put a lot of functions inside, which belong normally to a certain dedicated object on the primary side, like the motor or like the circuit breaker in our example here. For the distance protection, we have, for example, a function group line and so on. And here we see all the protection functions which are now located and also the settings. In the function group circuit breaker, I see here some general settings, but no protection function. And now I show you how easy it is just to add a protection function or an additional function. It's not really, it's a protection function, let's say. I want to add a circuit breaker failure protection to my standard configuration here, and therefore I go here on the right hand side. Under types, we have here all our relays, and I search here my compact device now, the SX800, and now I have to see I have here a function group circuit breaker, so I guess that there is the right function which I can put in here. And if I go here a little bit further to the right, I see here is a circuit breaker failure protection folder. And here is the 50BF function, and it's just simply as simple as now. You can see I just drag and drop this function and place it here on the circuit breaker function group. And now this function is added, and in the same way, I can also delete all the functions which I don't need. And if this function costs function points, I get the function points back. So this is basically how to model or to add functions and customize the functions I want into my configuration. Okay, let's have a look on the overcurrent protection functions quickly. So I double click here, then I get the settings a little bit distorted here. We see already I have here a graphic representation of my settings, so two thresholds at the moment here. So I can see this looks not really reasonable, I think. So I need to change something here. So for each major protection function, I have here a diagram where I can see graphically what I program here in my various stages. I don't want this here now, so I take that away. I have to click here on this triangle and then on this diagram. So I have just now the settings. Basically, we have stages in the overcurrent protection function, and we have a predefined number of already existing stages, but I can add more stages. So now with that maneuver here, I just add another definite time stage here, and now we have 3 of them, and every protection function has a maximum number of stages. Also in the distance protection, we call this stage, although this stage is basically a zone, but the basic naming is stage or auto reclosure cycle. We consider also as a stage in the naming, so don't get confused by that. It is what it is at the end. Good, and now here I can make the settings. So here you see I already added the values. Here I take the RMS value. Here I take the fundamental component. This stage here trips without any operating delay, and this here I delayed by 100 milliseconds so that the peak inrush current of the motor start does not trip that stage at the end, so that this stage can handle this. And the third stage here I could now set, I don't know now what is the nominal current of the current transformer, so I just need to guess here something. This seems to be small currents, I don't know. So this needs then to be checked in detail, and then here as an operate delay, then I need the starting time of the motor, 10 seconds maybe. So this is not really a reasonable protection function, it's just an additional thing I can do because the stage is already there. Okay. Under the power system, I have here my measuring points, just to mention that. Here I set the nominal current of the transformers, current transformers. Now it's 1000 amp. If I want to see what is my motor, then I go here on the general of the motor function, and then I see here I set up a motor with 1 MVA. So it's 91.6 amps and 6.3 kilovolt. So, and adapting to that, now I could adapt my current transformer saying, okay, maybe 100 or 150 or 200 amps. So I add this here, and in that way I set my current transformers. This here is the start point orientation of the current transformer, and with some additional features here, some fine-tuning of the current inputs, amplification factor, and some supervision functions at the end. And the same we find at the voltages. So if I want to define the voltages, then I need here to set my 6.3 volts, kilovolts, I mean, and the secondary voltage, for example, 100. And also further down here, I find, again, supervision functions for this dedicated voltage input. Good, so this is basically the workflow. I would like to show you now, there was also the question, can I protect more motors with one relay? Yes. This is not exactly what I have, but I have the case with the window type differential protection. First, let's have a look on the hardware. So it's first a 7SK85, so the modular device, and what I already added here is an expansion module with the current input, which I need for the window type CT. Or I can also put a window type CT here and use this for the rest. So this is completely free, and this needs to be configured just in the Dixie here. So I have one more current input here, and measuring points routing. Now you see I have two so-called measuring points. This is what I later connect with my function groups to have the protection function. And you see I just added here a second measuring point on the second current transformer terminal. This is basically the extension I have here. And now we have to have a look on the settings. We see here on the one hand this function group motor, which works with all these nice protection functions which come already from the application template. And what I did now on top of that is I created another box, another container, which we call voltage current three-phase. So this is a standard box for protection functions where I can put a lot of functions that need a three-phase current or a three-phase voltage or both. And what I need for this overcurrent protection, for this differential protection at the end, is an overcurrent function, and I place this overcurrent protection function here. I cannot put it in the other function group because this here is connected with a first current transformer, and I need another input for the window type current transformer, which I now decided it should be the second input here. How do I define this? There is one missing link, and this is the assignment now of these measuring points to the function groups. So, and this is what we see here, function group connections. Here I have basically the function group motor and the circuit breaker, and here is what I added manually afterwards, this function group voltage current three-phase, and you see the input here in this function group is just the current transformer for the input for the window type current transformer. So it's done by this connection here at the end. So this is basically the idea what we have here. In the second tab, I have a connection between my function groups and the circuit breaker. So also here I make this connection here. And now those two function groups work with different currents, but they operate on the same circuit breaker here. So this is basically what I define here in this Dixie. Okay, then finally, maybe a short word about the classical differential protection, which I put in here in this relay. So the hardware is pretty much the same. The structure is a little bit different. I have here a function group motor stator and a function group motor side. So in this motor stator, there are all the nice protection functions we have for the motor protection. And the motor side is a function which is just used to get current on the start point side of the motor protection. And then we have a function group motor differential, where the differential protection function is located. And you see here are the settings. Before we go to the settings, maybe I have one slide to show that structure here. And this is the same for all differential protection functions in cProtect 5, except the line differential protection, because there are anyway two different devices. And the busbar protection also does not go to that principle, but all the other differential protections like generator, motor, transformer protection, they have the same structure here. So I have here the motor stator with all the protection functions, the motor side for the second current transformer that comes in here. And they are internally linked to the motor diff protection function, where I have the stages of this differential protection, and this is then connected to the circuit breaker. I think this is now a little bit too far for those who have not yet worked with a Dixie, so I will just show that diagram on the slides, and yeah, very quickly maybe this is also done in the, I have to search that. Here, function group connections. So basically it is here on the third tab. I have my motor side, motor stator. They both get the currents from the different current transformers, and they both finally go into the motor differential function group. So this is a little bit a special architecture, but not very complicated. And if you once have memorized that, it's relatively simple. And with that structure, we can also make a differential protection of more motors, to come back to the question of the beginning. So then I would take two current transformers and one diff function for the first motor, then two more current transformer inputs and a second differential protection function for the second motor, for the third motor, and so on, whatever you like, until you come to the, let's say, the limits of the processor. A little bit the settings. So this is the operate curve. Here we can leave the standard values. The only thing I have to adapt basically is here in the starting detection of the motor. You remember, we put up the threshold by a certain factor. This is this factor here for a certain time. And this time is what I, no, wrong. Here is the factor. So I was in the wrong block here, starting detection and the maximum permissible start time. So this is the startup time of the motor. So if the motor starts up with 20 seconds, and here I have to be careful. If I have undervoltage situations, the startup can be longer. So I have also to consider this, that not during the startup, I retract or I drop off the tripping characteristic, and it becomes more sensitive. Again, if I want to avoid that. So I need here to enter the startup time, the longest possible startup time of the motor. And after that time, then the tripping characteristic falls back to the standard one, which I find here, which I define here in this operate curve with this couple of settings here. Additionally, I have a fast stage, which I can switch on here, and here the threshold is interesting. So this is now the standard value. I would set this threshold over the starting time, starting current of the motor. Yeah, because then I'm on the safe side. This is the most critical part here, and here I trip very fast. For sensitive, I have this stabilized characteristic here with a lot of features. Also a lot of features we could not discuss now to make the differential protection stable here. Okay, with that, I think I would like to finish the Dixie part. And I think now we have again a break. And before the break, question and answers.
Yes, and there are more questions that came in. All right, this would be a short questions round. because I think we still keep the question for the thermal image because that's after the
Comes
third part.
after the,
And so we just have one question currently that came in from OY. What is the transient dimensioning factor for the CT sizing and how to consider for the motor CT sizing?
The transient dimensioning factor, the KTD, is, okay, we have two IC standards to describe this current transformers. I picked out one where we have this ALF dash, and we have another way to describe the current transformers, and there we have this KTD factor. Now I need to go into the...
No problem, there you go.
Jump where do we have that stuff here? If I can get it here right from scratch. Here's the KTD. So here the definition is it's another IC standard. I need a certain required product KTD times KSSC. So the KTD in our case would be, if we go here to the differential protection, the KTD would be the 3 here, and the KSSC is normally the short circuit current divided by the primary current. In this case, okay, we have the requirement, it must be the transient starting current here. AM is the starting current. And what is important here for this definition is this required product, so 3 times this here, which is identical to the ALF definition we have here. So it's another way to describe current transformers, and they split this up in a certain way. So exactly the details, what is behind this CT definition in the standard, I cannot deliver you now. I just don't know that. Basically, it's another way how to express the current transformer requirement here and the performance of the current transformer when you have this in the data of the current transformer manufacturer.
Thanks, Klaus. And I think that will be part of the homework. Just send the link to the answer there, to the respective calculations. So that was a short question answer round for that. We keep the one that's already there. And I think we'll meet you in about, let's say about 7 minutes. So have a short break, give your eyes and ears a rest, and see you in a few minutes.
Okay.
Thanks for the info. So welcome back, and welcome back to the last part of the tutorial around motor protection. And now you will come to the interesting part around thermal protection and the configuration in Dixie. And once again, it's not me, it's my dear expert Klaus, who will explain the thermal protection information, share his knowledge around that with you and show the configuration. So Klaus, let's start again.
Yeah, let's attack the last part here about the thermal protection, overload protection of a motor. I spent some extra slide to explain, let's say, the theoretical background, and then we go for the settings. So basically, where do we have thermal overload protection of the motor? On the one hand, I have the protection of the stator. The stator gets stressed normally during normal operation. So if you go above the nominal current only with a small amount of current, we see that later, then this brings the stator to the thermal limit. Then we have the rotor, which we need to protect. For the rotor, the normal operating condition is not critical. So the temperature is relatively small under normal operation compared with the maximum temperature the rotor can have. The rotor is stressed during the startup because there we have high currents for an elevated time. So there can be the problem that I have a too long start, or even the rotor does not rotate at all when it is locked during for the machine or whatever the process what is behind. And I can have too frequent starts. So if I cannot start one after the other, so I need to have some time in between the starts of the rotor. If I do this too often, then I also overheat the rotor. And then there is another stress of the rotor. This is the negative sequence amount of current. Here, it's already a relatively small share of negative sequence current that heats up the rotor. This has to do with the equivalent circuit of the rotor, but let's save that for the second session in May, because let's concentrate first on the stator. Okay, and I can have overheating of the bearings, as already mentioned before. Here we have just a temperature measurement. This we cannot detect from the measurement of the current that flows into our motor here. And yeah, already mentioned at the beginning, thermal overheating of the plant if there is no load on the working machine in some cases. This we can detect with an undercurrent function. So that means the current is too small or smaller as it should be normally, and then I can give a warning or trip the motor on that. Good. So basically, overload effect in general, I have somewhere a power that I bring into my object. Now I talk about an object first, because this principle is the same we use for all different kinds of object, also for the transformer, for a cable. It's always the same function here, also for the rotor with some changes, modifications. So I bring power into the object, and this is basically the power loss. So this is the wiring of the stator now, and also the iron losses. They look also like a resistance in the equivalent circuit. So both bring me power into the motor, which does not go out onto the working machine. So the motor heats up. And the energy I bring in must go somewhere. We cannot accumulate forever. And the motor will not heat up forever because I lose also power again. And this is due to the temperature difference of the motor and the surrounding, the ambience. And this is what we have here. Here it's marked with CV convection. So normally it's an air stream that goes through the motor and cools the motor, but basically it's everything that goes outside. Okay, the single body model, you see I put here a skidding symbol. Now it becomes a little bit theoretical. We will have a differential equation, but for those who are interested, okay. For those who are not familiar with that, don't be too frightened. I will come to a relatively simple summary at the end. As often with the digital relays, we have a lot of background and the setting is relatively simple, and it's here the same thing. So what is the basis of our thermal protection functions? It's always an equivalent model, and in the so-called single body model, what we have, following this IC standard here. So here, the single body model is described. And if you know the electrical circuits, what is a current source and a capacitor and a resistor, then you can easily understand also this equivalent model where we have a current source in the electrical field. Here, this current source now is a power. So this is the power I bring in, the power losses, which I have in the motor to heat up the motor. Then I have a thermal capacitance. This is like an electrical capacitance. And I have a thermal resistor here. This is like an electrical resistance. And I have here a voltage symbol, voltage source symbol. This is a temperature difference in the thermal world. So basically, if you then consider also the units for the various things here, then you can say a power is pressed into that motor, into the thermal model. This is the current losses, the power losses due to the current, the heating up of the motor. And then this, the motor has a certain capacitance. That means it does not heat up suddenly, but the temperature rises with a certain time. And there is energy stored in this higher temperature. Here is a temperature difference. And the part of this power goes via the resistance here and creates me here in the electrical world. This would be a voltage. If this is a current, here is a voltage. In the thermal equivalent model, the power here through this resistance creates me a temperature difference. This is what goes out of the motor into the ambience, basically. Good. Yeah. This equivalent model does not really describe really precisely exactly what happens in the motor, because there we do not have just one block of iron and nothing else, but we have the copper windings, we have the iron, we have a stator and a rotor, we have the ventilation, and I have a resistance, thermal resistance between the copper wiring and the iron, from the iron to the outside, from the iron to the ventilation inside to the rotor. So there's a lot of mutual coupling, and it is cannot be described exactly just with one capacitance. This problem is for all kind of thermal models with a motor. Simply, we could use such a model, but we don't get settings for that. So if we apply some model to describe something in the motor, we need also to get the quantities that we do this in the right way. And this is just not given by the motor manufacturers. By the motor manufacturers, we get normally the maximum current we can bring into the system and a time constant. So this is an approximation, but it works. It's used widely. It's part of a standard here. And so it describes at least the requirements we get from the motor manufacturer in a satisfying way, although it's not 100% precisely. Okay. So now what can we do with that model? We don't have all these quantities from the motor manufacturer. So we have to transform that in a handy way so that we have only a couple of settings and we can describe what is allowed for our motors. We have a differential equation, as already mentioned. I don't go into the details. So basically, it's a description of what's going on here in this model. And we calculate here always with the temperature differences here consequently. Refer to a reference temperature, theta 0, which is 40 degrees. Okay, we want to get a dimensionless equation first. So we have to standardize on something. And I take here the steady state part. And not only this, I say I want to standardize on the maximum power under reference conditions. What I can put into the motor. That means the ambient temperature is identical to the reference temperature. And then the maximum power I can press in here without that the motor gets destroyed or overloaded. And this is my Pmax 0. So this is the value I want to standardize. And you see here the theta 0. Yeah, okay, the delta is missing, but the delta is here, then the ambient temperature is 0. So this is fine, this equation. So yeah, okay, the theta A is identical to theta 0. So that part here falls off. And then I divide by this value here. So this is just a trick. Now I get dimensionless values in this equation. So that's the first step. Second step, still the skidding symbol. So we are not yet finished with the theory. This is the equation we had before, and I know now this is too fast to trace everything step by step. This is a little bit homework if you're interested. I think the steps are fine enough so that you can follow from one to the other and make your own calculations. I do this a little bit faster because maybe not everybody is interested in that. Okay, so this is the tau, the thermal time constant. It's this R times C thermal. And this here we call theta in capital here. And Here I have the ambient temperature with a theta in capital. If we have a closer look on this power ratio, then we find out the power is proportional to the square of the current that flows into a resistance. So for both sides here, numerator, denominator, so the ratio of the powers is equivalent to the ratio of the currents to the square. This is a very important finding and relation. And here we see this K times IN. K times IN is the maximum current which I can put into the motor so that it does not overheat. Especially here now, keep in the background the stator or also other equipment. As I said, the transformer, it's the same story. So this here, I have an abbreviation still, the J, a big J, and this here is K times IN, the I max 0 here. And then we come to a differential equation like that. So this looks already much more handy. And for those who understand differential equation, you know, there's a solution. This is just written in another way. There's a solution that goes with an E function, exponential function. Basis is E, the number E. And yeah, if we have a closer look on that, I put it a little bit in another form. Then we see here, basically, well, maybe here you cannot see it, but if you go into that formula, you see the following. This E function starts at a certain starting temperature, and this is this theta 1. Yeah? And it ends at a certain end temperature, theta 2 here. So that it goes up like that as an E function. And how fast this goes up, this is defined by tau. So the time constant, which you see here, so tau or tau thermal, which you see here or here in the equation. This is basically what happens to the temperature if you add a certain new temperature, which is defined. So the theta 2 here you see is here's the current inside, and here is additionally an ambient temperature if the ambient temperature is not equal to the reference temperature. So I have a jump in the current. Square of the current ratio gives me then here the theta, the temperature, the dimensionless values of the temperature, and this gives me then here the end temperature as we see. This can also go in the other way around. That means I have a lower end temperature. For example, the motor is running and then you switch it off. Then there's no current flowing in anymore. So this J here is 0. And then the temperature goes down in the same way, you see, just from here to here. Both is possible depending if the end temperature is bigger or smaller than the starting temperature. And that's basically what we need to understand when we check, for example, verify this, this function. We normally put a current in or an overcurrent, and then we see that the temperature follows like an exponential function here. In reality, when the motor is running and I have different loads, then of course it will not be just one E function. Then I will have successive small E functions always when the current is changing. Then the temperature follows like such an E function depending on the temperature difference and the time. And this is what we do basically in the relay. So we don't calculate with an E function. We use the differential equation as a basis at the end, but that's detail. So the relay is always tracing what is the current doing and then always calculating according to these equations the temperature that comes out from that. Good. Summary of all that. If the current is K times IN, then the maximum temperature here, the dimensionless value, the normalized value is 1 plus possibly another ambient temperature. So if the temperature goes up, then of course I get a higher value and I cannot bring so much current into the motor so that I do not overshoot the maximum temperature. Okay. What else? All values are dimensionless values. And to define now our protection function, basically I need only 2 values. The first is 3 values, the nominal current of the motor, then the permissible overload factor K. This is normally given by the motor manufacturer. Typical values are 1.1 or 1.05 or something like that. and a time constant. So, and these are the basic three values which I need to know, basically just the k and the tau, for the setting of this function. And all what we encountered beforehand here is in the relay. So this is just, let's say, the side dish of the meal, let's say here. Okay, what is important is a permanent thermal image is available. That means we trace permanently, right, when you start to close the breaker and the current starts to flow into the motor. Then we trace the temperature all the time. If the motor is running, then the temperature will go down again after the startup. If you have a heavier load, then the temperature will go up. So we will always have an actual, real image, calculated image, thermal image of the motor temperature. And this is the difference to a simpler function where I have a threshold and then I start to calculate from zero the temperature, which was a practice a long time ago with the analog relays or the simpler relays. Here we do it in a better way. So how do we come to the tripping time? Very quickly, if I have a constant current, overload current, then I can make the following calculations. If the current is moving up and down, of course, then it becomes more complicated. But for testing, you normally inject a constant current, and then you are curious if you have a certain temperature already there, what is the tripping time until I reach the end temperature? Okay, so this is basically again our E function we had before, and the tripping condition is always that my theta is 1, the temperature is 1, dimensionless. That means the temperature in the stator has the maximum temperature, which is allowed at the end. Okay, and then I can calculate here the tripping time by solving the equation with 1 here on the left-hand side. And now we have to think about what is theta 1 and theta 2, because we would like to express this with currents. And the theta 1 is the preload current to the square times Kin plus the theta A if there's another ambient temperature. And the end temperature is pretty much the same, but here's then the new current. So I could also say I2, but it depends on I here, the formula. So therefore, I just leave the I. And if I insert all that stuff here in our tripping time, then I get this here basically as the tripping time. Maybe you know these formulas already from the manual. The theta A here, the ambient temperature, is only here in the denominator, not up here. If you make that calculation and the theta A shows up here, then you made some mistakes, or have a look again. This is really the formula that fits, and the relay is also working according to that formula. I also made the thinking error at the beginning, at this theta A also here upwards on the numerator. This is really the correct way to express that. If this theta A is 0, then we don't care about it. Then this formula here simplifies. And if I say I start from 0, so no load, preload condition 0, and the temperature is 0 in the motor, then I have again a slightly simpler formula here at the end. Good. If I don't get the time constant from the motor data, then I can estimate this time constant. Normally it's given by the motor manufacturer. Sometimes you get a pair of current and maximum time the motor can withstand this current, overload current and an overload time. So it's not really a time constant, it's a couple of values here. And yeah, we can define the K factor first. So the K factor we need. If not, then I hopefully have a maximum current available, which I can permanently put into the motor without overheating it. And from this, I calculate the K factor. This is what we basically had before. And for the tripping time without preload, I have my formula now from before. And what I now do is I insert here my maximum time, T, and I insert my current here, which I get because I get an overload current and an overload time in that case. And then rearranging here, solving that equation, I get here my time constant tau. So this would be one way to estimate the time constant if you don't get this from the motor manufacturer. Okay, here I put an example. I think if you're interested, then you can go through that. It's basically inserting the values into the formula just to have an example. Here I would like to point out a couple of items which I think are worth to mention it. So again, I have this formula here, and this is the E function we were already discussing here, and the temperature here goes up depending or in the way of this, following this E curve here, this exponential curve. And if the temperature reaches here 1, then there will be the tripping condition for this function. Maybe some findings, some relations. If I put not the maximum current inside, so K times IN, where, so this is the formula, K times IN will lead me to 1. If I put in just a nominal current, if I have a look here, then I have here remaining 1 over K to the square. And this is a temperature under nominal conditions. This is what I wrote here. And if we think about standard K factors, we find that, for example, for 1.1, K factor 1.1, the temperature in this model for the nominal current is just 83%. And if the K is 1.05, it goes up to 91%. Because it goes with the square of the K. So this is one finding. The other finding is, if you think about the tripping time, depending on the injected current here, we can find a fixed ratio to the tau, to the time constant. What does it mean? Let's make an example. I get a tripping time, which is identical to my time constant here. So 1 is the ratio. If my current divided by K times IN is 1.258. So you can get this also when you solve that equation. And yesterday I put some other values here because I wanted to see a little bit how this looks like. And it could be helpful if you don't want to go through that calculation, just look here at that table. And if you make a setting for your tau and you inject then 1.258 times your K times IN, then you will arrive with the tripping command exactly after your tau value, the time constant value. And if you inject a higher current, then you are tripping faster because then here the curve is steeper. I think this is logical. And if you want a tripping time of 1% of the tau, then you need to inject 10 times the maximum current, for example. So in that way, you could test the behavior of this exponential function in the relay and not waiting, for example, 900 seconds or longer if you inject just a little bit more current than allowed for the very long values of the time constant we normally have. So here's the behavior. Again, the advantage we have when we have this preload consideration, so also called thermal model with a memory. The memory means what has happened before we get the overload situation. And basically, if you follow that formula, you see the higher your preload, the shorter is the time until you reach the tripping condition here. And this is what we do and calculate dynamically. I think there's not much more to say in that slide. Okay, I would like to give you some advice or let's talk about some situations. One is if we consider the ambient temperature. This is not done very often, or it's not done very often with a sensor. We have the possibility to add a sensor and measure the ambient temperature and bring this into this calculation. Or I have another ambient temperature. Permanently, the temperature is higher than the 40 degrees. Then I need also to know what to set now. Do I need to modify the K factor or what shall I do? Therefore, here are some considerations which guide you to the right conclusion at the end. So this is what we had already. This is the steady state equation with a K. Now I call this K0 because this is normally given for the reference temperature of 40 degrees. And what I said, and then I solve that equation, then I bring the K over here and make the root. And if I say my maximum temperature is 1, then I get the formula like that. So again, a little bit fast, but I think it's a relatively simple solution here, what I do, calculation. And this Imax A is now the maximum current under another ambient temperature, different to the reference temperature, you see. The reference temperature goes here into the calculation under the root. So I call that Ka times In instead of K0 times In, which would be the appropriate factor if the ambient temperature was really the 40 degrees, the reference temperature. And then I get this here as a result. What do we see here? If now my ambient temperature is smaller than the reference temperature, so this theta A, this normalized value smaller 0, then my Ka is bigger K0. That means I can put in more current into the motor. It's clear because it's colder outside, so more power goes out of the motor, and the other way around. So if my temperature is bigger than the reference temperature, my Ka is smaller than K0. That means I cannot put in so much current into the motor because it's already hot outside. Here's an example. I don't go through that example in detail, just to mention one thing. I need an absolute value in the calculation for this theta A, because here we calculate all with relative values based on the assumption that everything runs under reference temperatures. If you now go out of that frame and say, no, we have another absolute ambient temperature, we need somehow a relation. What does this mean? Refer to the maximum temperature of the motor. So I need then an absolute value, maximum temperature of the motor here. And then I can make such a calculation. Often this maximum temperature is not given, but you get a temperature rise for the nominal current. So what is the temperature difference in the motor in Kelvin if I put a nominal current inside? This is another quantity what I can get sometimes, and then I can calculate a maximum temperature out of that with such a formula here. So I don't have here the proof how we come to that formula, but it's a relatively simple thing. And in that way, you can also get the maximum temperature. And with this here, this goes into the calculation of my theta A. You can then get another K factor for the other temperature, so maybe 20 degrees, like in that example here. Okay, so now we have two possibilities, either when it's permanently just 20 degrees and not 40 degrees, then I could set the K factor to a higher value, so the one which I calculate here, like that. We have another possibility. The other possibility is to say, okay, the K factor is always the one under reference temperatures, and I have a setting here called default temperature, and here I can set the ambient temperature, which I normally have, or which I permanently have, or for which I want to set up my protection function. And this is normally the biggest temperature I can have, because then I have the smallest, margin for the current. So the current is then the smallest value which I can put into the motor if the temperature is the highest one. So I just set this setting default temperature. The name, I think, is not really completely lucky, because what is meant is the ambient temperature here. So an ambient temperature setting, if the ambient temperature is different to the 40 degrees. This is called default temperature because, as already mentioned, I can also adapt my thermal model dynamically to the ambient temperature when I know this temperature. So I can also put a sensor somewhere outside measuring the ambient temperature, and then bring this sensor inside in the relay and calculate it. Okay, why do I have then a setting here? Yeah, simply if that sensor measurement does not work anymore, sensor is broken, the wiring is cut or whatever, then the relay needs some temperature to continue the calculation, and this would be the default ambient temperature. It's called default temperature in the settings here. So then the relay comes back to that value and continues to calculate with that value. If the ambient temperature measured before the last one is smaller than that value, if the last measured temperature is higher, it stays at the higher value. So you see the tendency is always to go on the safe side, not to overload the motor. Therefore, it's called default temperature. So basically, we have a dedicated setting, not called ambient temperature, but called default temperature. So if your motor is running permanently under 55 degrees instead of 40 degrees, set the standard K factor, which you get for the 40 degrees, and put here then 55 degrees Celsius inside. And then everything is fine. Then the thermal model will calculate or take into consideration this other ambient temperature. Good. So recently I had a case where the motor data was not for 40 degrees, but the K factor was for 50 degrees Celsius. And therefore, we need to make a small trick. And the trick is relatively simple. You know already the formula. Now we say the K0, this is the K factor for 50 degrees, which I get from the motor manufacturer, is my reference temperature. And I want to know what is the K factor for 40 degrees. And this is the calculation. So basically the same calculation, you need the maximum temperature, and that's it. So what I need to do in that case is I set the K factor according to the new calculated value, and then I set the ambient temperature as it is in reality, 55 degrees, or I connect the sensor again and measure the ambient temperature dynamically. Okay, here's an example, and I don't go over that example now in detail, again, because the time is a little bit lagging. Basically, let's think about, I have my K factor for 50 degrees, I have an ambient temperature for 55 degrees, and here I have a temperature rise, or the over temperature at the nominal current. Then I can follow this calculation. So I calculate a K factor for 40 degrees. Then I set this parameter to 55 degrees, the default ambient temperature, and the relay does the rest. So basically, this is what we need to adapt to all these situations here. One last slide for the K factor and the temperature classes. Often the motor is defined or designed according to temperature classes, which you see here. And the insulation is designed for class F, and the motor is running at the class B. So here you see the temperatures, and from these temperatures, you can calculate the K factor according to that equations here. So you see, assuming that example, we get the K factor calculated of 1.13. So the 1.1 again is a reasonable value here. These are the settings. I think I discussed the most important one, those here. We have here the possibility to enter a cooling time constant when the motor is at standstill. So the cooling down, because the ventilation is missing, is slower. Therefore, I can set here another value. Typical value would be 7 times the tau, the normal time constant. This is the current setting below which this standstill is applied. Then I have warning thresholds, drop-off threshold, behavior when the device is powered off. So should I store the thermal replica, the thermal image, or no? So we recommend to store it. Then it's stored for a certain time. And then the question is, one point which I did not mention is, how shall I handle this thermal image when I get very big currents during the startup, or if there is a fault inside? As I mentioned before, this is a simplification of what has happened or what happens in the motor. That means not all the situations are described in a perfect way, and therefore I can have an overreaction of this model during the startup, or if there is a short circuit current. And to overcome this, I can say, okay, the stress is described, the stress of the stator is described well when I have normal operating conditions. In case of a fault, this model here can overreact, and therefore I can set here a limiting current, saying, okay, if the current is higher than X, so this must be a short circuit current, then I want to limit this current influence to a certain value, to, for example, 2 times the nominal current or so, in order not to make a wrong tripping during the startup or under special conditions of this model here. And this is the current value what I have here. And then I have the story here. When I use the ambient temperature, this is my temperature rise at the nominal current. I can enter a minimum ambient temperature, so I don't give more power into the, don't allow to give more power into the motor if I'm below this ambient temperature here, for example. And this is the selection of the temperature sensor. So these are basically the settings which I have. The standard ambient temperature, of course, default temperature, as we discussed before. These are the settings of this function here. Again, maybe as a summary, this function works for the stator, and for the rotor, we have a dedicated separate function here. I have here also a short explanation about the signals that we have. I leave this here in the documentation for you. And also here some measurement values, also here described on the slide as a documentation. So if you're interested, you can have here a short look on that slide. So I try to explain the most important measurement values which we have that concerns here the overload function. Good. And with this, I would like to end the third part of that section. And we have definitely one question to answer.
That's true. I'm glad you remember. And if you do not remember the question, here it comes again. It came in from AN rather early, and it was, what are the capabilities for CProtect 5 motor protection for thermal image modeling of the motor and the number of starts per mission?
Okay, so first one, as I already mentioned, we have a dedicated function for the stator, the one I was talking now. We have a similar function for the rotor. This comes in the second session. And there we have basically 2-3 different functions for the rotor. The one is a startup supervision. That means this is against too long starts. We have what is it called? The function 66. Don't remember the name now.
It's like ordering at a restaurant, you know the numbers instead of the name of the function. But I think it's somewhere hidden in the manual, right?
It is there, and the name will come.
66 is, yes, it will.
The restart inhibit function, now it comes back. And here we describe how many starts from the cold and warm start situation, or warm situation of the motor we can do. So this is a separate function. And then we have again a function also for the rotor. This is for the negative sequence, and they run all independently of each other. So we have dedicated functions for dedicated problems in the motor.
All right, thank you. So currently I see 3 more questions, and I think we just take them into and keep you a bit longer in the line. Thanks for staying with us, because SL wants to know, hello, please explain the setting of the functions. And now here comes in this numbers again, the 48, the 66, and the 51M in the Dixie. So that's a specialist right there.
Yeah, I can only say, please switch on again on the 2nd of May. There we talk about these functions.
Perfect.
Now we don't have time. So there I will put it also with example, hopefully with formulas if you like them. There we will have them the details of these functions. So we saved that topic for the next session.
Perfect. I love it when the question fit into what we planned for you, because that means we deliver the right stuff and you will get answers to your questions. So join in on the 2nd of May to get an answer on the settings of dedicated functions. 2 more questions are there. Does it make sense to activate the thermal image if we have temperature sensors like PT100 in the motor?
Yeah, the PT100s you have at certain places, and let's say the thermal image, this overload function, is running in parallel. So it is, let's say, it monitors, let's say, the temperature of the motor based on the given data we have. So the maximum current we can bring into the motor, for example. And the temperatures have at a certain place the temperature. So I see it that it should go in parallel. So you normally have temperature sensors in the bearings, also for the for the winding in the stator. But additionally, this thermal overload protection function should run in parallel to the temperature sensors. And the input is not much. It's just the currents which we anyhow measure, which go into the motor. So you can just activate it. It's not an additional effort you have there.
All right. Thank you. And then one last question. What are typical time constant values for 6.6 kV, 500 kilowatts, 3 megawatt
2 3 megawatt.
Kaka motors? I hope that you know more details on that. Now I'm out. I know kilovolts and kilowatts and megawatts, but what about those motors? And can a general range be given?
Yo, this is difficult. Yeah. So
Also for the expert.
for this data, we have normally time constants around in the minute range, so 5 minutes, 10 minutes, 15 minutes, 20 minutes, 30 minutes, something like that. And this depends on the size. So I cannot give you now just a general number because this could be also completely wrong, like just half the value which is there in reality for a certain motor. So this, please ask from the motor manufacturer, or if you don't have it, maybe in one slide there was a way to come to this time constant when you have at least a pair of settings of values, maximum current, maximum time, then you can calculate the time constant, which you then can insert in our function here.
All right. Thanks a lot. Thank you for your active participation. I think we need another slide because now the question and answer round is gone. Let's see. Yeah, that's the contact. That's perfect because you will get information on the contact to Klaus, how to contact Klaus if you have special questions or if the answer was not exactly what you expected, just contact Klaus. You will also get access to the recording and to the presented slides. I think you've seen a lot how to protect your valuable assets, your motors. I look forward to seeing you in the next session around motor protection. We already learned it will happen on the 2nd of May. And if you cannot make it there, yeah, you missed the chance of asking your questions. But yes, there will be another recording. So for now, I'd say stay safe, keep your systems protected, and see you next time. Goodbye.
Bye.